Bozeman. I will be introducing our speaker today. It is Dr. Stuart Maloy from Los Alamos National Laboratory. Dr. Maloy is the team leader for MST8, which is the group that deals with materials at radiation and dynamic extremes at Los Alamos National Laboratory. He has worked there a number of decades and is the Advanced Reactor Core Materials Technical Lead for the Nuclear Technology Research and Development's Advanced Fuels Campaign. And he's also the NEAT Reactor Materials Technical Lead for DOE-NE. He holds bachelor's, master's, and PhD degrees in materials science from Case Western Reserve University and is a registered professional engineer in metallurgy. He has applied his expertise to characterizing and testing the properties of metallic and ceramic materials in extreme environments, such as under neutron and proton irradiation at reactor-relevant temperatures. So the extreme environment being radiation fields and radiation damage. This experience includes testing the mechanical properties, such as fracture toughness and tensile properties, of a variety of materials, to name a few: modified 9-chrome 1 moly steel, HT9, which we'll be talking a bit about today, stainless steels 316L and 304L, Inconel, and some others. Testing them after high-energy proton and neutron irradiations using both accelerators and fast reactors to provide the damage. He also has done characterization of materials after testing, which includes using transmission electron microscopy for analyzing defects such as dislocations, twins, and second phases, and using high-resolution electron microscopy to characterize defects at an atomic level, and also doing nanoscale mechanical testing. Dr. Maloy has a lot of peer-reviewed technical publications and numerous presentations, and we are privileged to hear one today. Welcome, Dr. Maloy. Let's welcome him.
Thank you, Alan, and thank you all for this opportunity to speak to you today. As Alan led into about some of the progress that we have been making on developing high-dose radiation-tolerant materials for nuclear applications, and along with everything that he said that I've done, I have a lot of collaborators that have done a lot more than that. And they're working with me at Los Alamos National Lab, working with me at Pacific Northwest National Lab. And I'll point out, I guess, a lot of the different areas as we go through the talk as to where, if you actually make a note to look in the lower right-hand corner, you can actually see where a lot of this research is actually being done. It's not all being done at Los Alamos National Lab. With Bob Odette at UC Santa Barbara and Dave Holzer, collaborator at Oak Ridge National Lab. And then that list gets even longer when I look at all the different contributors that have helped with, for example, hot cell research at the labs, or pulling out the high dose irradiated material at Pacific Northwest National Lab, or helping with making a new heat of HT9 at Idaho National Lab, helping with the ODS material development, and then a lot of university collaborators from here at UC Berkeley. You'll actually see some of the in situ micro tensile testing that HEVO actually did on some of the materials here. Also collaborators at Case Western Reserve and international collaborators as well. So a large number of people working together on this. And for those that were here 10 years ago, you remember this slide. Because 10 years ago I actually gave a talk here as well. I wanted to show this because, to be honest, actually we've made some of this progress. That was sort of nice to see, but also wanted to look at my old slides and make sure I'm not presenting the same thing, which I'm not. Don't worry about that. But back then, in 2007, we were working on developing materials for advanced burner reactor, and we've gotten and tested a lot of these materials now out of these different STIP irradiations. We would like to say I've already got these matrix materials. That would have been right after the radiation stopped, but we're still trying to get them shipped back from France. So So that's done, but they're not back at Lanley yet. I'm hoping that FY18 it'll actually get here. Well, the part that we're doing a lot of research on right now that I'll talk about in this talk is the structural material qualification, the high dose testing of HT9, and also the advanced structural material development. That's the development of oxide dispersion strengthened steels. And back then we were looking at making a new fast reactor called the advanced burner reactor in 2020. That's not part of this program right now, but there is plans for a new test reactor that many of you might have heard of, this versatile test reactor. That the hope is that we could actually get that built in the U.S. by 2026 with a lot of funding added to it. So a lot of these things actually did happen, and I'll summarize where we are now in the area of structural material qualification and advanced material development. So why are we looking at developing improved radiation tolerant materials? The main aim in this program of now Nuclear Technology Research and Development, I should point out that in those slides that I showed before, we've gone through, I think, 4 name changes right now. But now we're on Nuclear Technology Research and Development. But the main aim there is to enable a multifold increase in fuel burnup over the currently known technology. So we know that we can push HT9, we can push ferritic martensitic steels to fairly high doses, even out to about 200 dPa. But for the ultra-high burnup fuels, we'd like to push the burnup to 30 to 40% burnup, which means the dose in the cladding could be out to 300 to 400 dPa. So it's really a grand challenge to get out there. And in order to do that, there's a lot of things we'll have to overcome. The interaction between the fuel and the cladding. If it's going to be in the reactor for maybe 10 to 15 years, you could have significant interaction between the fuel, especially a metal fuel interacting with the cladding. So there we're developing coatings and liners to prevent that from occurring. I won't talk about that in this talk. We're also the development of improved radiation tolerant materials. That's what I'll talk about mainly in this talk, and that's development of improved ferritic martensitic or tempered martensitic steels centered on HT9 and oxide dispersion strengthened steels. There are some advanced alloys that people are starting to look at as well. I'd be happy to talk to people afterwards about them, but the main 2 sets that I'll talk about are ferritic martensitic and oxide dispersion strengthened steels. And then they need to be corrosion resistant in the coolant. What we're looking at is sodium as the coolant, but there are reactors, advanced reactors that use lead, and they're, as you know, I think in the groups here, lead is a little bit more of a challenge than sodium is. But sodium, if you can keep the oxygen level very low, below 10 ppm oxygen, then the ferritic martensitic steels don't really have an issue. But if you go to an advanced alloy like an oxide dispersion strengthened steel, you could worry about whether sodium is going to actually pull the oxide out of the surface of the material. And that's one of the things actually we're looking at in some of our materials that we're making right now. But if I really wanted to retire, I'd develop advanced materials completely immune to fuel, neutrons, coolant interactions, and then we'd have no issue. But I'm not there yet. I'm working toward that. So what's a brief outline? I'm going to talk to you about qualifying HT9 to high doses, where we are, a little bit of background on radiation effects of materials, but then get into how do you get high dose material data. It takes a long time in reactor, and I'll talk to you about different ways to get there. Developing one new heat of HT9 that we're working on, and some information on interstitial effects in ferritic steels. And then I'll get into the advanced radiation tolerant materials, mainly centered on oxide dispersion strengthened steels. So I think most people know this background, but clearly when a high energy particle comes into a crystalline material, it can interact with the atoms and cause a large cascade, transferring the energy into the atoms and the atom structure, and then following that, making in the cascade, you have of course, a very large area of vacancies and interstitials. But then, of course, after that displacement spike relaxes, then you end up with a large number of vacancies as well as some interstitials left in the material. And of course, that's happening continuously under high dose of radiation, and eventually can build up a large number of defects interstitial and vacancy clusters, which eventually lead to dislocations and maybe also precipitating out new phases, and can lead to changes in material properties. And we want to be able to know that, be able to predict that, and be able to develop the best materials that can resist that sort of radiation damage under high doses.
Did that second picture also come from Brinkman's article?
Actually,
No. Okay.
I'm not sure about that. I
Okay.
haven't checked on that. Because this was
Long time ago.
added, but yeah, I need to check on that. But after high dose radiation damage, it can also lead to some failures in nuclear systems. High dose radiation damage in the case of these ducts led to significant swelling, which led to failure in these duct materials. Of course, it can also, with mechanical interaction, can lead to some fretting or actual failure of cladding materials with the radiation and mechanical interaction. And then with corrosion, there's significant things that can happen with the chalk river unidentified deposit, or crud. It's identified, but anyhow, yeah, crud in the reactor, which isn't good, or corrosion in the head of a reactor that's accelerated by radiation. So these are things we want to avoid, so we want to try and develop better, more radiation tolerant materials. I'm not going to tell you that these materials apply to all those applications, but there are specific high dose applications like cladding material that this material would apply well to. And what is HT9? It's a tempered martensitic steel that has a ferritic lath microstructure. This is an optical micrograph of a typical tempered HT9 microstructure, and it's got a fine distribution of laths that are tempered to ferrite, and there you can perhaps see there are carbides at the boundaries, and there are also carbides at the lath boundaries as well. That large number of interfaces in the material serves as sinks for defects, and it's also all ferritic, so it's a BCC structure, which also helps from the standpoint of a reduced void swelling in the material as well. And this has been known for a while. This article back in '82, where they noted that the difference between a austenitic stainless steel like 316, another austenitic stainless steel D9 that has titanium additions to it, and then HT9 and some other variants, which showed significantly reduced void swelling. This is effluence, but down here you can see the translated DPA. It's about 80 DPA. You can see that we're 5% swelling in a D9, or even almost 30% in 316, but HT9 is very little. And one of the things we're working on is how do you know when HT9 actually starts to swell, because it actually, there isn't very much high dose data way out here. So that's the question. How do you get very high dose data on materials? In a typical fast reactor, you can get in the core about 20 to 30 DPA a year. So if you want to test the material at 200 DPA, you've got to irradiate it for 10 years just in the reactor, not including the time it takes to take it out and do the PIE on the material. If you want to go to 400, you're going to almost 20 years, which is past the PhD generally, I hope. So how do we get this data? There's significant data that we're trying to pull together to understanding what the better materials are after radiation to high dose at specific irradiation temperatures. This is the Nuclear Systems Materials Handbook, which has significant data mainly on austenitic stainless steels out to about 100 DPA. This is some data that we recently got from this program, the ACO3 duct, where we received the material from the fast flux test facility and got data on an actual component out to 155 DPA. These are more materials that we actually retrieved from FFTF Materials Open MOTA, which is Materials Open Test Assembly Irradiations. So that gets you out to almost 200 DPA. And then this new irradiation we just did in France, in the matrix, called the matrix radiation in the Phoenix reactor. That's new material out to about 75 DPA. So none of these are really getting us out to this 400 DPA that we would like to get to. So how do we get out to greater than 200 dPa? Well, one of the ways we're doing this is we're actually taking specimens that were cut out of the ACO3 duct and put them back in the reactor. In a collaboration with TerraPower, we're radiating specimens out in bore 60 to very high doses. Right now we're probably at about 250 dPa or over, about 200 dPa on that material. I'll talk to that in some of the next slides. But that's all going to take a long time in a reactor. So one of the other ways that we do this, and I think people here in the crowd also do this, is through high dose ion irradiations. You can get good data. You can get data to high doses, but you get it over a very small volume, and it's because of the difference in dose rate. You have differences between what you're measuring in ion radiation and what you actually measure in reactors. So you have to translate that, or try to translate that to actual reactor data. And along with that, to do that, you need improved model development, which some of that is going on within the nuclear energy research, and I think hopefully that will continue to move forward and be improved in the future. So one of the ways we're doing this, though, to try and get data in reactor is we've taken some materials. This is previously irradiated materials at temperatures from 370 to up to 600 degrees C, and pre-irradiation doses out to 155 dPa. And we put pressurized tubes, tensile specimens, TEM specimens, Sharpie specimens back in the reactor. We ship them to Russia in a irradiated material shipment, and those are being irradiated. The target dose is up to 450 dPa, and we'll be doing PIE at Lamel, Oak Ridge, and Pacific Northwest National Lab. So that's one way, one hard way, which is going to take some time to get that data. Let me also talk to you about some improved materials that we're working on. We had a new heat of HT9 made that following just typical NQA1 standards, and we did tensile testing on those materials after radiation, and it turned out that this HT9 material showed almost over 5% uniform elongation at an irradiation at 290 degrees C up to 6 dPa. So it retained ductility in typical area where you don't see much retention in ductility. And all these other materials, T91, Urifert 97, NF616, and F52H, all were irradiated at the same time. They all show a drop in uniform elongation to about 1%, as you can see in all these curves right here. So something was better about that material that we've been looking at. We also did some ion irradiations to high doses, and that's about it now. But ion irradiations out here to high doses, and you could actually see that this material also did fairly well from with respect to swelling resistance as well. So we made some new heats of material. We made 2 by Metalworks and 2 by Sophisticated Alloys, and we're controlling the interstitial content in this material. And mainly what we're looking at is, can we control the nitrogen content? And this is how, other than looking at all the other differences, this is the main difference that we could see, is nitrogen content between this material and the other materials. And why do you think that we centered on that? Well, there's actually a lot of work on interstitial content in ferritic steels. This is just a typical ferritic steel, exactly the same alloy, one where they heat treated it and quenched it to leave nitrogen in solution, and there you see strong Luder's band formation and low drops in the beginning of the, or localized deformation in the beginning of deformation of that material. And then the other was heat treated and reacted, the niobium was reacted with the nitrogen to pull it out of solution, and you can see you completely remove that Luder's band formation. So you can, by going to a low nitrogen alloy, you can reduce localized deformation in a ferritic steel. And we know that for typical irradiated materials, the reason why you tend to get reduced elongation is that the uniform elongation, as it reduces, you tend to get very localized or defect-free channels within the material. So is it possible that the nitrogen is locking or vacancy clusters in the material, making them, in a sense, stronger strengthening sites, but making them making more localized deformation when you go to deform that material. I don't know. That's something that we're looking at. So we've taken some materials and made heats that, in this case, is sort of a control material that's got 12 chrome, 0.2 carbon, and 0.05% weight percent nitrogen, and then another low nitrogen that had 0.001 weight percent nitrogen. And clearly what we're trying to look at is, does nitrogen impact radiation damage, but also what impact does it have on deformation? Our differences in solute atom concentrations, like nitrogen high versus low, observable in terms of the deformation behavior. And this is just some radiation damage microstructure in a high nitrogen alloy that you can see here. You can see that the effect of nitrogen, it doesn't really affect the last structure of the material, but what it does affect is that we did have enough nitrogen that we're precipitating out some nitrides in the material. These are these chrome nitrides in the high nitrogen material on the right. And you don't see, of course, that in the 0.001 weight percent nitrogen with a low nitrogen alloy. So we know we maintain the last structure, but we have a significant difference in nitrogen content in the material. And we're starting to do, hopefully this will work, but we're starting to do some in situ straining studies on the material. And this is the low nitrogen alloy, just looking sort of down the lath, and you can actually see fairly uniform movement of dislocations, actually down the lath, across this, from one side of the lath to the other. If you move, actually this, I don't think this one's going to work, I think, but on the next slide I have one, so yeah. But if you move to the high nitrogen alloy, here you can see, if you sort of center on this region right here, you see pretty localized deformation, although these dislocations are on sort of within the foil, going from top to bottom across the foil. But you can see one set of dislocations go through, and then another one go to follow it through the material during deformation. So there's the leading dislocation. You can see it sort of pops through the material, and then right behind it you've got almost 2-3 more that are moving through it through the material. So it appears that we're seeing more localized deformation in the case of the higher nitrogen alloy, but now we're starting to do this this is without irradiation. We're starting to do this now on the irradiated materials to look at how the effect of nitrogen has on localized deformation of those materials. And then what we'd like to get to is actually doing microtensile testing on these materials. What you'll see here is more of an effect of the last structure, not the effect of nitrogen here, but that's also interesting. And that here's HT9 in the unirradiated case, and that's about a 2 micron wide tensile specimen that EVO actually did here. And you can see fairly uniform deformation before failure on this tensile test. But when you actually do it after radiation to about 1 dPa, you see very localized deformation, but this happens to be right on a boundary. So that makes it a little bit more difficult for us to do a microtensile test, because we've got the lath boundaries we have to deal with as well. So we have to find areas where we don't have lath boundaries and do a similar test like this. But it clearly shows that the lath boundaries, you can get localized failure as well. So that's where we stand right now with testing some new improved heats of HT9. Hopefully by controlling the nitrogen content, we can even push it to higher doses, especially in the lower temperature regime. The other area, though, is can we actually make even better materials through putting a fine oxide dispersion within the material. And that, I'll summarize that in the next couple of slides, and also tell you where we are in making the heats, but also making them into actual engineering shape, which is pretty difficult when you get to these improved radiation tolerant materials like this. So these materials, they're also named nanostructured ferritic alloys. They have a very fine dispersion of yttrium, titanium, yttrium, oxygen, nano features with numbers up to 6 times 10 to 23 per meter cubed. And this is an atom, an APT image on the far right side of that, of a material that, well, a heat that we made at Los Alamos in collaboration with Oak Ridge and UC Santa Barbara. And there you can see all of these fine areas, if I could actually point it out to you. But on the right, you can see those fine areas are about 2 nanometer size oxide particles that are uniformly dispersed within that tip that we did atom probe tomography on. The advantage of these nano features, typically they're Y2 Ti207, is that they serve as sinks for defects, so sinks that can service places where you recombine the interstitials and vacancies under radiation, therefore reducing the number that are actually within the material and reducing its amount of hardening under radiation. But also they serve as improve the creep resistance of the material as they block dislocation motion within the material. So they make a stronger material, but they also make a material that's more radiation tolerant. So why have we don't you find these easily produced by industry? Well, it's a pretty tortuous process you have to go through to make these oxide dispersion strengthened alloys. So you take an alloy powder, in this case it would be 14 chrome with titanium and tungsten added to it, and then add yttria to it. Well, the yttria doesn't want to go in solution, it's a large atom. So the only way you can get it to go in solution in the ferritic matrix is to do a high intensity ball mill of the material. And you guys have one here from Zaz, but these attritor mills, you have to run them for almost 40 hours to force the yttrium in solution. So it doesn't want to go in solution, but you can force it into solution, and then once you do that, if you either hip it or extrude it, so in this case we can it in a steel can and then extrude it at 850 degrees C, then you can precipitate out those oxides in the location where the yttrium has gone into solution in the grains. And now you get a very fine dispersion of 2 nanometer oxides within the material, which is great. But now you have to try and extrude that into an engineering shape, which, being a high strength material that it is, it's very difficult to do all the final machining, the final extrusion processing properties on these materials. So we're making some progress, but we're not there yet. Here's material that we've extruded now into long rods, which would then be further extruded into tube form. Like I said, these were initially ball milled by Zaz in 15 kilogram batches, and then we took the ball milled powders, put them into cans, evacuated the cans, and then extruded them at 850 degrees C. And in some cases, we had to even straighten them afterwards. Then we need to take that material to extrude it further to make tube forms out of it, and that's one of the difficult processes. We've also extruded them into plate form and then cross-rolled them. In this case, the material was cross-rolled to 50% reduction in thickness, getting it down to about a 10 millimeter thick plate, and then continued to actually cross-roll at 1,000 degrees C down to 5 to 2 and down to 1 millimeter. This actually went really well. There was a 95% reduction in thickness, and there was no edge cracking in this material. So for a difficult material to process, that went very well. The reason why we wanted to take it down to 1 millimeter in thickness is that we're trying to test the way you'd weld this material and the way you'd actually weld it on a thin sheet, which one of the processes is to do friction stir welding, which mixes the material without melting it. If you were to melt it, then all the oxides are going to go back, are going to collect, and you'll have large oxides in the material again. So you want to do this without actually melting it. And this is a bead-on plate weld that was actually done, a friction stir weld going across a plate to weld 2 1 millimeter thick plates together. That went fairly well, actually. You can just see here the stir zone versus the sort of the heat affected zone off to the right. You don't really see much difference at all. We're doing a tensile test on this material. This actually looks, I won't show, but this actually, that data looks quite good as well. So we're making some progress in learning how to weld that material. But how do we actually make it into tube form? Well, one of the ways that we've had some progress with is doing hydrostatic extrusion, but it's a pretty long, drawn-out process. These are all the outer pieces that go on top of our little tube. So this is our 14YWT NFA. It's put on a mandrel. It's got a sleeve of 316L on both ends of it. It's got a liner that goes over the top of that, and then another copper nickel alloy cladding that goes over the top of that. All that's put together to get your hydrostatic stresses so that you can hydrostatically extrude that material. But then in one pass, you can hydrostatically extrude it at 815 degrees C in one run at a 4:1 extrusion ratio. And then you can end up actually with a material much longer with thin walled that you could actually do some testing on. So it's possibly a way to get to final tubing, but it's a pretty drawn out process. I can tell you that even after you get done with the extrudate, this is the Oxide Dispersion Strengthened steel area. It's got all the extrudate over it. So you have to go through etching it with 40% nitrate for about 2 or 3 days. And once you've etched off the material, then you end up with a nice tube. This is about a 10-inch long tube that was extruded out of Oxide Dispersion Strengthened steel. And we can do some tests with that. We can do look at whether we've got a uniform dispersion of oxides throughout. We can look at what the texture is. So it's nice from a research standpoint, but it's a difficult way to get there from a industry type standpoint if you want to make something affordable. So that's one way of getting the thin wall tube. The other way that we'd like to get is through cold pilgering, and many of you might be aware of this. This is what is used for making zircaloy tubing. It's in a sense what you're doing is you're extruding the material by deforming it in compression. So you can take a material that's not very ductile and you can extrude it to fairly long lengths. They use this for titanium tubing, they use it for zircaloy tubing, and they can get 9-foot long tubing routinely, and this is what we use for the nuclear industry. So can we do that with the Oxide Dispersion Strengthened steel? Actually, the groups that are working on this in Japan and in France are successfully doing that. We're not there yet, but we're hoping that we'll be there soon. I can show this to you. This sort of gives you a little bit of a diagram showing you as you're rotating the tube and pushing it through and compressing and extruding it in a sense at the same time. You slowly, but you end up with a very long tube at the end. You can actually Pilger process down to a thin walled tube. And through working with Sandvik, through collaborators at Pacific Northwest National Lab, they have been successful in Pilger processing MA956. So that's a fee crawl ODS, an iron carbon aluminum ODS, and there it doesn't have as fine of an oxide dispersion. So we started with that as something to sort of test the process with. They were successful with that. We've done some short lengths of 14YWT, but we're not there yet for longer, thinner walled tube. And just to point out, why are we looking at these materials? As I pointed out before when I showed you HT9, it maintains its ductility after low temperature irradiation. Now, this is the same irradiation, but we put MA957, an oxide dispersion strengthened steel in there. And we also put some 14YWT that was extremely high strength. This is over 1,500 MPa yield. It didn't get any worse, so it maintained the ductility it originally had after radiation, but I think the real promising one is this MA957, where you can see after 6 TPa 293C, it's over 5% uniform elongation. And it actually didn't even harden that much. It went up by about 200 MPa, unlike the ferritic martensitic steels, where the hardness increases by almost a factor of 2 after radiation. So it really does show promise, and through some high-dose ion irradiations, we've irradiated our 14-WT material sort of down here, and all the way out to 500 dPa from ion irradiation at least, but compared to HT9, it's still not swelling yet. So it really does have a lot of advantages, but we still have a bit of a ways to get there to get it to actual engineering forms. So I think with that, I'll summarize and just tell you a little bit about our future work. We've made a lot of progress on making some improved HT9 materials. The new heat does show retention of uniform elongation after neutron irradiation. And we also, through looking at some controlled heats, we're trying to understand whether, what connection interstitial impurities do have on localized deformation before and after irradiation. We've made a lot of progress on developing improved radiation-tolerant nanostructured ferritic alloys. And I should point out, if anybody is actually working in that area, there's a special issue on nanostructured ferritic alloys that I'm guest editor on in crystals. And if you want to publish your work, the abstracts are due in March. But we have a large heat of 50 kilograms of nanostructured ferritic alloys that was made, and we're doing a large number of extrusions of rods and thick-walled tubes all the way down to at least the plates down to 1 millimeter. Made some successful hydrostatic extrusions at Case Western, and also as I pointed out, ion irradiation testing as well as the low temperature irradiation testing shows that these are very promising materials. What are we working on now? Can we get further on Pilger Processing, especially collaborating with P&L and Sandvik, and also we are collaborating with the French and the CEA on that as well. And can we get some high-dose data on these materials? So we actually have some of the tubes that were sent to Oak Ridge. So we will be doing some irradiations on the hydrostatically extruded tubing at Oak Ridge. So we'll get about 8 dPa a year. And maybe in the future we can, through collaboration, perhaps get some irradiations in fast reactors internationally, or maybe in the versatile test reactor when that's built within the U.S. So with that, I'd be happy to take any questions.
Ferritic steels and H9 in particular were the darling of the fusion materials community for about 10 minutes in the early 80s. You remember what happened, why they're no longer as popular?
I don't do a lot of work in the fusion area, but maybe you can add to it as well, Mike. But I think one of the issues that fusion has that they don't have in fast reactors is that you have a large buildup of helium along with displacement damage at the rate of 10 ABPM helium per dPa.
Right.
And what the tempered martensitic steels don't have is a fine oxide dispersion that can help you to manage the helium. But the ODS steels do. So I think partially they've moved toward that direction. I'm not sure if there's other reasons why they may have.
Yeah, well, Zinkel was here last year and he was pushing ODS as a remedy for that. But
ODS acts as a surfactant for helium. But the other problem is that you got a fantastic amount of hydrogen in the first wall as well. And things start to change dramatically when you also introduce the hydrogen.
I understand that's right behind the helium as the primary problem.
One of the problems that's sneaking up on us with ODS is that you get ballistic decomposition of the ODS, which releases free oxygen into the material. And there's been some observations where you form very hard oxides because you now have free oxygen migrating in the material, and that also changes mechanical properties. So one of the questions at these high doses is that whether the ODS can itself sustain the radiation damage.
Yeah, we've done some high dose, and the high dose ion irradiations that we've done on our ODS alloys, and it's actually similar to what other people have seen. Between 400 and up to about 600 degrees C, you still see the oxide particles uniformly dispersed within the material. We do see a slight reduction in size, but we don't see a complete loss. So, I mean,
No.
nobody knows what's happening. I mean, maybe the oxide particles are going in the solution and precipitating.
Exactly.
But at low temperatures, where you run into that issue, and I think it's below 300 degrees C, where you can actually start to, you put the oxide particles into solution, but they don't precipitate. So that's where you could run into an issue where you actually lose.
On the low temperature side, you get in trouble.
Yeah, but it's not really an issue for fast reactor application. That's not really an issue. You're not running the reactor at that temperature. For fusion, it might be an issue because they do have
Cold
some
places,
areas
yeah.
where they get dose at low temperature.
So on about 2 or 3 slides back, you showed a comparison. No, that go forward. Yeah. So you said I saw a number 0.2% swelling per DPA. Huh?
Yeah,
That's in the HT9.
yeah. And then
Do you know? Have you characterized the cavities or what is the source of the swelling? Is
I
it?
mean, we've looked at it, and this is measured with TDM.
Oh, it's okay. So it's measured with TDM.
Yeah, we just don't. I'd like to know what it is for the ODS steel, but it's not there yet.
Okay.
What kind of dBA per year can you get from BOR?
From bore 60, you can get about 20 dPA per year. That's pretty good. I mean, it would be nice if we could have gotten some irradiations in Joyo, where when they're running, they don't run a full cycle for a full year. They usually run about 6-month cycles. When they were running, you could get over 30 dPA per year at Joyo. But with that, over that 6-month period, so it's still evened out to about the same.
Well, what happens when you have a refractory period like that, where you're on it, you said you're recycling some old materials that sit on the shelf simply for years?
Yeah.
Does that affect the results at all?
As long as when you shut the reactor down, you keep it at a low temperature and you don't heat it back up to a temperature near the radiation temperature, is where you anneal out some of these defects. So, you know, we've done other irradiations where we shut it down. As long as it stays cool, those defects don't go anywhere. You heat it back up to that reactor temperature and continue, you can get the equivalent to a long-term irradiation at that temperature.
So not everybody in the room has some material science background. Can you explain the difference between the austenitic and steels and the ferritic martensitic? And you mentioned swelling being one difference in this case.
So, I mean, in general, in a steel, you can either stabilize it in the austenitic phase, which is face-centered cubic phase, or you can stabilize that in the BCC, or body-centered cubic phase. And mainly that's through controlling the nickel content. So if you have a high nickel content steel, just like your typical stainless steel, then you get fully austenitic phase in the material. If you pull the nickel out, then you can get to, and you keep the chrome level high enough, you can still have a stainless steel, but it's fully BCC phase. Why is that important? In general, from void swelling that you run into is one of the main issues in a material. In an FCC material, you tend to nucleate voids faster, and you also tend, once you've nucleated them, so you nucleate them at say 50 to 70 dPa, so you nucleate them at an earlier dose, and then you run into the steady state swelling regime faster, so you get to a steady state swelling of about 1% per DPA fairly quickly in an austenitic stainless steel. In a ferritic stainless steel, which has a more open crystal structure, it takes longer to nucleate voids. So you don't nucleate voids in a ferritic steel like HT9 till over 200 DPA, so as you see here. And once you've nucleated them, they start to grow in a steady state regime, which is what we call here the steady state swelling regime here. It's only swelling at 0.2% per DPA. So it's still a lot. I mean, clearly, once you get over 5% void swelling, typically from an engineering standpoint, you don't really have something you can use much, but at least you'd only take off at 0.2 versus 1% per DPA. So if I put the austenitic stainless steels on here, they would be swelling here. And so ferritic steels push you way out to here. ODS, perhaps somewhere even further.
One more quick question, because we have a lot of people who are interested in, at the beginning of your talk, you mentioned new advanced reactors pushing to those higher DPA levels. What kind of engineering considerations should the reactor designers be thinking of with regard to materials that you're mentioning here?
Well, I mean, so it depends on what the reactor, well, in one case, it depends on what the reactor radiation temperature is. Just like when we were talking about the difference between a fusion reactor and the difference between a fission reactor. Because the radiation temperatures in a fusion reactor range from 100 degrees C up to 1,000 degrees C, you run into a large number of different regimes, you might say, where you can run into materials issues from low temperature embrittlement at low temperature to high temperature helium embrittlement above 600 degrees C. So when you start looking at other reactor concepts, it's not just dose that you need to look at when you're pulling out the right material for this application. You need to look at what that temperature window is in which the material is operating. I mean, for example, I didn't show the plot of properties versus dose that were measured on an ACO3 duct. But so the ACO3 duct, we irradiated in FFTF from an initial radiation temperature of 380 C out to 500 degrees C. If you look at the data that was measured between 410 and 500 degrees C, out to 150 DPA, you saw almost no swelling, no hardening in the material, really not much of a change. So if you pick the right window, you don't have significant issues to deal with. But if you look at that small window between 380 and 400 degrees C, the hardening was about a factor of 2 increase in the yield stress, and we had significant reduction in ductility just in that little window. So it's critical to look at the doses, the average dose that the material is going to see, but also what is the radiation temperature, because that really controls what the final defect configuration is in the material, which controls how the mechanical properties are changing.
Are there any other questions? Well, Professor Hostman has had a long collaboration with Dr. Maloy, and as you mentioned, you've been to Los Alamos. Who else has been to Los Alamos? Okay, to work with. Okay. But as Dr. Hostman continues his work, he may end up having more students, right, out of Los Alamos. So.
Yeah, I open the invite to all of you, if you guys happen to be working in the similar area, please, and you're at the point where you think you want to do a semester or summer or something like that in Los Alamos, we can find a place for you. Please send me an email. I mean, I don't know if I can find it, but maybe there's others within my team or within my group that might have some interesting projects for you to work on. But really, we really value the collaboration and the research that we get and the work that we do with students in Los Alamos. It's really a critical part of our research.
Let's thank Dr. Maloy.